Hello, this is Identifying Malicious Activity in Network Traffic for Data 670 Data Analytics. My name is Daniel Yukua under Professor John McKeeby. So the point of this data analytics project, or the problem I should say, is the data analytics problem that I'm analyzing is how to identify malicious attacks in network, i.e. how do we go ahead and segregate these malicious attacks, and then we go ahead and categorize them from the benign and normal network activity. So the importance of this project is really to, 1, reduce business disruption, 2, to allow cost savings and risk reduction, 3, to enhance our network security, and then 4 is to have compliance and regulatory requirements. Once again, all of this comes down to, can our user access our network? This is reduced business disruption. If a hacker or any malicious group is allowed inside of our network and is allowed to go ahead and shut it down, we are losing business, we're losing reputation, we're losing potential future contracts, and we are not complying with the standards and the regulatory requirements that have been set before us. And so all of these are extremely important, and the crux of it is we don't want our network to be ransacked. We want our network to be up and as secure and robust as possible from these attacks, and to minimize the downtime and to minimize really the disruption that we are giving to our users because of this. So the way that we're going to do this is we are going to take a model. We're going to take a machine learning model and we're going to go ahead and train it. We're going to use two models, one binary classification, and then another one is a categorical classification in order to segregate the attacks from the normal benign activity and to furthermore segregate what type of attacks they are. And the three key performance indicators that we're going to be using in order to test the success of this project is 1, model accuracy to the current data, 2, model accuracy to the new data, and then 3, the speed of identification in both models. So what does the data look like? What is the description of the data that we're going to be using for this model? Well, what we're going to be using is what's known as the CICIDS2017 dataset. It's a comprehensive network traffic dataset with a realistic representation of network activity. It's a large-scale, high-dimensional data, and it has a size and shape where it is one set with 8 various subsets ranging in size from 170,000 to 692,000 rows, totaling 2.8 million rows of data with over 79 features. So what does the data look like? Well, with again over 2.8 million rows, we have 15 class labels, 1 basis and 14 attack, 1 being like the benign number of instances, and then 79 features that include destination port, flow duration, total forward packets, total backward packets, etc., all the way down to the label. And as we can see on the right hand side, we have 15 different labels, one of them being benign and then the rest being bot, DDoS, DOS, GoldenEye, DOS Hulk, etc., all the way down to web attack. As you see over here, we have a data visualization that's representative of a bar and whiskers plot of the distribution for flow duration. As you can see, there's a very clear divide and separation between benign and attack. This isn't always the case, but these are key indicators or key features that will show great separation between the two in the binary classification. As we can see with these two different visualizations, we can see the disparity between the distributions of the different types of attacks. So in the first one, we have attack versus benign with nearly 20% distribution, 20% being attack and then 80% being benign. And then furthermore, we have the different distributions between the types of categories of attacks that we have seen. So even furthermore, we have very greater disparity, with SQL injection and SSH being very, very minuscule in their representation. Now, as we can see over here, there's a huge disparity between not just the benign and the attack, but also between the different types of attack themselves. For DOS Hulk, we have over 230,000 instances, while Heartbleed only boasts a small number of 11 instances. So in order to counteract this, what is going to happen is that we are going to combine these types of attacks and categories into aggregate categories in order to have a higher classification accuracy for the models. So for this data analysis strategy, we're going to be using a two-model approach. First and foremost, we are going to put the first into model 1, which will separate and filter benign versus malicious. Once malicious activity has been filtered out, it will go into a second model, which will then categorize them into the different types of attack that we have laid out beforehand. The three types of models that will be utilized in this project will be logistic regression, random forest, and neural network. Each of these models will be tested independently and then combined with each other dependent on the results that the models produce. For instance, we will need two models in order to create the champion aggregate model. One model will be used in order to have binary classification between malicious and benign, and then finally the next model will have use for categorical classification. These models are utilized because they have great categorical classification, and if combined with one another could prove to have a great amount of utilization for our application. Starting with logistic regression. It's the simplest model, it's the easiest to understand, and it's highly iterable. Logistic regression makes a great binary classification for our first model. It allows us to have a highly iterable model that can be updated and reformed later on and switched out quite easily. Neural networks, on the other hand, are one of the most powerful models that we can use. It's great in handling high dimensional data, such as the one that is provided within the CICIDS2017 dataset, but it works a lot like a black box. We don't exactly know what is going on with the connections between the two of them, and on top of that, it is not as iterable. It takes a long time to generate a new model with updated values, and it takes hours to go ahead and train a new one. Random forests, on the other hand, are more understandable than neural networks, still considerably powerful, good at handling high-dimensional data. Because of this, they make a great addition for Model 1 with the binary classification and Model 2 with the categorical classification. The champion model for this particular project was neural networks, simply because of the high accuracy that was achieved by using neural networks. Some results that came about from logistic regression. One thing that we found out very soon was that it was not computationally complex enough to really accurately categorize the data as correctly as we may have needed it to be. May be useful later on in a binary classification model, but does not really warrant further exploration. In the case of the neural network, we had a longer waiting time. We waited hours, but because of that, we also had a higher accuracy. We could also refine further the model to achieve an even higher accuracy, especially within the categorical value of model number 2. Random forest boasted also some great numbers, was faster than the neural network, but still lost out when it came to raw accuracy. Has some more potential accuracy with more tuning. However, I believe that in general, the neural network will go ahead and reign supreme and edge out the random forest. The accuracy of the neural network makes it a real primary choice for both the binary and the categorical classification. The random forest has a viable potential to beat it as a champion model. However, the neural network always seems to edge out accordingly. Logistical regression was simply not capable of dealing with the sheer complexity of the dataset. Some recommendations, specifically for the logistic regression model. Continue to fine-tune binary classification. If this model cannot exceed or even match the accuracy of the neural network, it will then be cut. However, if the logistical model does meet the accuracy of the neural network, it could be considered as a replacement for the binary model. This is because of the iterability that the logistic regression model has. It is faster to go ahead and redeploy and retrain a logistic regression model than to have to constantly retrain a neural network. Some further recommendations for the neural network. 1. Continue to fine-tune hyperparameters in order to increase accuracy. I believe that there is still extra room in order to increase accuracy, especially within the categorical model. 2 is to experiment with other models to increase the combination accuracy and to integrate them with the neural network in order to be able to create a brand new higher accuracy aggregate champion model. Another thing is that once the model is actually trained for a neural network, the actual classification of new entries is actually quite fast. Some recommendations with the random forest is to continue developing random forest model to increase accuracy. And then if that accuracy of the random model can really be comparable to the neural network, random forest should be implemented instead. New threats are constantly emerging, and the ability to redeploy highly accurate models becomes increasingly advantageous. So for instance, neural network takes hours and could be even later on take days to train. If a new type of threat occurs and is presented to us, then we should be able to retrain our models and then redeploy them as fast as humanly possible. Random forest, with its lower training time, might be able to do that. However, another thing is that if logistic regression happens to go ahead and beat the random forest as well, and especially in the binary classification, then that should be used instead. Some lessons learned here. The neural network was the most accurate, but took the longest time to train. Random forest was faster to train, still not particularly fast, but was comparable in accuracy to the neural network. Logistic regression did not at all have the ability to accurately deal with the complexity of the data when it came to the binary classification, or especially with the categorical classification. Some next steps with the implementation as a perspective. Number 1 is to start test phases on real network activity and observe if normal network activities are being disrupted. If normal activities are being disrupted, we should adjust the network model as necessary. Number 2 is to stress test the network with random types of attacks and identify holes in the network model, and then, once again, adjust the model as necessary. We're going to repeat steps 1 through 4 until we have an acceptable network that complies with regulations. And then finally, as a 5th step, is that when new types of attacks are discovered, we're going to retrain, redeploy the models with the new types of attacks that are identified. Here are the references that are utilized within this presentation. And then finally, are there any questions?